Hey guys, today I want to present the solution to the China Team Selection Test 2016 problem 4 from test 1. At first, let's have a look on the problem statement. We are given two natural numbers c and d greater than or equal to 2. Now we define a sequence ai as follows. a1 should be equal to c and an plus 1 is defined as an to the power of d plus c for all integers n greater than or equal to 1. Now our task is to prove that for all integers greater than or equal to 2, we can find a prime number p such that p divides an, but p does not divide ai for all I less than n, so for I equal to 1 up to n minus 1. After seeing this problem statement, it's clear that we want to investigate on the behavior of prime divisors on this sequence here. Therefore, let's consider an arbitrary prime number q, but in such a way that q divides at least one of the sequence members, because otherwise it's not interesting for us. Let's now use our recursion to figure out what this tells us about the divisibility by q for the other members in our sequence. So we get that ak plus 1 is equal to ak to the power of d plus c. This is actually really nice because ak is divisible by q, and thus this is congruent to c modulo q, which is nothing but a1. Taking a closer look at this, we can get an even better statement, because we see that since ak is divisible by q, ak to the power of d is divisible by q at least d times. Therefore, this equation here also holds modulo q to the power of d. Right now, we only use the fact that q divides ak at least once. But if q divides ak more than once, we can get a better result here. Thus, I want to define b to be the number of times q divides ak, so b should be mu q of ak. This implies that ak to the power of d is divisible by q b times d times. Therefore, this equation here also holds modulo q to the power of d times b. We can see that this equation here tells us that our sequence ai is periodic modulo q to the power of d times b with period k. This motivates us to choose k minimal. As I said, our sequence is now periodic modulo q to the power of d times b with period k. Thus we have that ai plus k is congruent to ai modulo q to the power of d times b, and thus we are able to calculate mu q of ai for all I only in terms of a1 up to ak. Namely, by the minimality of k, this is equal to 0 if k does not divide I, and otherwise this is equal to b. This tells us that each sequence member is divisible by q by at most b times, and thus we are motivated to try to get a solution for this problem using size arguments. The given equation tells us that an minus 1 is less than an to the power of 1 divided by d. Now we can use this inequality here recursively to get at first that an minus 2 is less than an to the power of 1 divided by d squared, and so on up to, in general, an minus I is less than an to the power of 1 divided by d to the power of I. Taking a look at the product of all the ai from I equal to 1 up to n minus 1, we get that it is less than the product from I equal 1 up to n minus 1 of an to the power of 1 divided by di, which can be written as an to the power of the sum going from I equal 1 up to n minus 1 of 1 divided by di. We can bound this from above by letting the sum here go from I equal 1 up to infinity to get that this is less than an to the power of 1 divided by 1 minus 1 divided by d, and since we start by I equal 1, we have to multiply by 1 divided by d. This is equal to an to the power of 1 divided by d minus 1, and now remember that d was greater than or equal to 2, and thus this is less than or equal to an. If we denote our product on the left-hand side by p, then we know by this argument here that if a prime number q divides one of these elements here, then mu q of p is greater than or equal to nu q of an. Together with this inequality here, we get that we have to find a prime number p such that p does not divide our left-hand side, capital P, but p has to divide an, and this is exactly what we wanted to prove, and therefore we are done.